Alright, lesson 109, conductor types, ampacity, overcurrent protection, type NM cables, and common voltage systems. I'm going to spend most of my time in this video honestly talking about ampacity, overcurrent protection, and you're going to notice here again we're reading a lesson in EWR. We're in EWR chapter 4. It's actually two sections. They want us to skip a section in the middle. So you're going to read 95 through 108. Stopping at voltage drop. We're not touching on voltage drop today. That's actually going to be lesson 110 coming up here. But then you're going to pick up after voltage drop, so pick up at 113 through 125, starting at non-metallic cables. So anyway, again, over here you have, as I said, chapter 4. Again, a lot of stuff in there. Don't worry about the voltage drop for today. I do want to spend some time here because we're going to spend a lot of time in our code book here at this point. So in particular, we're going to introduce ourselves to table 310.15b16, okay? Very important table. If you're going to memorize one code article, one code table, this would be a good one. I suggest you try to commit that to memory, or at least get pretty familiar with where it's at and how to find it. So what you're going to see here is essentially how much ampacity can any given wire size handle safely at various temperature ratings, okay? So first thing to notice, along the left side here we have our various conductor sizes, 18 through actually what they call 2000 kc mil. You might have heard it as MCM. Either way, it means 1,000 circular mils. So we call this a 500 kc mil. Metric K means 1,000, okay, kilo, and then cm or c mil means circular mils. That's just a measurement of wire. And then the old way you'd see that again, 500 MCM. Same thing. M is the Roman numeral for 1,000, so it's MCM. Either way, it's 1,000 circular mils. Okay, so you notice we're going to have 18 gauge all the way up through 1 gauge. Then we have what we call 1/aught, 2/aught, 3/aught, 4/aught, and then we get into our circular mils, 250 through 2,000 circular mils. Okay. You're going to see too we have two basic categories. Left 3 columns are copper wire, right 3 columns are aluminum or copper clad aluminum. Pretty much just call that aluminum. But then within each copper and aluminum section we have a 60 degrees Celsius, 75 degrees Celsius, and 90 degrees Celsius temperature rating. That essentially relates to your insulation type. So various insulation types of wire, as notated by these various acronyms here, have different temperature ratings, okay? And we'll talk about more on that when we get into doing some calculations here in a minute. And then of course, as you get down into the actual table, it's going to tell you how many amps can that particular wire, that particular size, that particular insulation handle safely. Okay, so we're going to use this table to reference what size wire do I need to run for any given load. You're going to use that a whole lot. Okay, last thing I'm going to point out to you is this little note down here. Refer to 240.4D for conductor overcurrent protection limitations. So we're going to go over to 240.4D over here. Going to tell us is small conductors. If you guys are following along, this is page 70-94 in your code book. So anyway, small conductors, unless specifically permitted in 240.4E or G, the overcurrent protection shall not exceed that required by D1 through D7. Long story short here, so for a 14 gauge copper wire, the biggest breaker I can put that on generally is a 15 amp breaker. For number 12, we'll skip that aluminum. Number 12 copper, largest breaker is a 20 amp. For number 10 copper, largest breaker is a 30. Those are 3 values you got to commit to memory. A 14 gauge is good for 15 amps. 12 gauge is good for 20 amps. 10 gauge good for 30. You'll notice something you might find funny if we actually go back to 310.15b16. What do we see here? A copper, let's just use 12 for instance. We said that was good for a 20 amp breaker. Well, here in this 60 degree column it's good for 20. We go into the 75, it's good for 25. And we go into the 90 degree column, it's actually good for 30. Keep that in mind when we come into derating factors. That will come into play. But you need to know generally offhand, 14 gauge wire is good for 15 amps. 12 gauge wire is good for 20 amps. 10 gauge good for 30. Okay, so keep that in mind. We'll come back to that. Alright, so again, lesson 109, I'm going to just hit a few key points I think are pretty important here for you guys. First, the insulation types. You notice all those various letters, and I don't need you to really memorize these. I just want you to know that they all mean something, and maybe we can sort of correlate some things. So the most common is actually called THHN/THWN. It doesn't mean your wire has two different insulations. It's the same thing. It just depends how you're going to use it. Probably the next most common is actually called XHHW, which is an aluminum wire, but that's, again, you don't really need to stress on those details. But I just want to explain what do those letters mean. So if we have that wire and we're using this THHN, the T simply stands for thermoplastic, tells us what it's made of. The HH, some people say it stands for high heat. I like to think of it as kind of two heat ratings, right? So it starts at 60 degrees. In the 60-degree column, we can add one heat rating, we go up to 75, add another heat rating, we're now up to the 90-degree column. And when we look, THHN is in the 90-degree column. So again, we have 60 degrees, we add one heat rating, we go to 75, add the other, we go to 90. Now I mentioned that applies in dry locations only, and we'll hit that when we get to the THWN here in a moment. So then the N simply stands for nylon. Again, it's sort of what it's made of. But if it's THWN, again, it's the same insulation, it just depends how we use it. T still stands for thermoplastic. H, we have one heat rating, so THWN you're going to find is actually in the 75-degree column. We basically lose one heat rating if we're in a wet location. So we can only go from 60 to 75. Your W then stands for wet location. So essentially, if I'm using THHN/THWN in a wet location, it's really only 75-degree rated. If I'm using it in a dry location, it's technically 90-degree rated. Okay, and then the N still stands for nylon. No big deal. Again, I don't need you to really stress over what that means. The biggest thing, any W in your insulation type is going to mean wet location. But other than that, know that we need to look for the proper insulation in the proper temperature column of 31015B16. Alright, so keep that in mind. So just quickly here, sort of an aside, some common voltage systems they're going to talk about in your text. The most common, I grabbed the three most common: 120/240 volt, 120/208 volt, and 277/480 volt. Okay, so what do all these mean? And you'll learn in year 2 there's about half a dozen more that are fairly less common, but they're still out there. So our 120/240 volt is single phase. What that means is there's only two hots. Why don't they call that double phase? I have no idea, but it's called single phase. It means we have two hots. Okay, we're going to have a neutral. Anytime you have a slash voltage, so 120/240, we need to have a neutral involved in there. And almost all systems are going to have a neutral, that, and everyone we talk about this year does. But if I take a voltage reading from any one of those two hots to the neutral, I'll get 120, or the lower voltage. If I take a reading between the two hots, I should get 240, or my higher voltage here. This is typically a residential voltage, so in your house, I would bet anything you probably have a 120/240 volt single phase system. It's almost the only voltage in homes in America. So you get your 120/208 volt. You're going to find that's a three-phase system. And again, if you guys are working in any commercial spaces, offices, banks, restaurants, more than likely you're going to have a 120/208 volt three-phase system. So again, we can sort of apply the same logic. If we measure from any hot to the neutral, we'll get the lower voltage of 120. If we go from any hot to the other hot, we'll get 208 volt. And in a three-phase system, we're going to actually have three hots. Okay, that's why it's three-phase. So from between any of those two hots, if we put our voltmeter, we'll read 208 volt. And again, that's a common commercial systems, think retail, things like that. And then 277/480, also very common. Three-phase once again. As you can hopefully guess by now, hot to neutral we get 277 volt, hot to hot we'll get 480 volt. And this is a lot more common in your maybe heavy commercial to industrial ends of things. So any kind of production, any factories, a pretty good chance they're going to have a 277/480. And they do actually go higher than that, but again, you'll learn more on those systems in year 2. But for sure, those are the three most common, and probably the only three we're going to need to reference for our year 1 studies here. So next one here, we want to hit on conductor ampacities. What does that mean? I think it's obvious. Maybe you think it's obvious, but let's make sure we're all playing on the same field here. So defined as the maximum current in amps that a conductor can carry continuously under conditions of use without exceeding its temperature rating. So basically that wire is not going to melt and burn up, right? It's safe, it can carry the current, nothing to worry about. Okay. Again, that information comes from 310.15b16. There's that table once again, or part of it anyway. So next up here, ampacity corrections. All right. So what I mean by this is, we know that normally this wire can handle, say, 50 amps, but because of some condition, it's not going to be able to handle that many amps. What conditions are these? Why would we do this? We're going to study two of the main reasons. If we have more than 3 current carrying conductors in a raceway or cable, we have to do an ampacity correction, or more commonly known as derating. Okay, it's not rated for as many amps. The other reason is high ambient temperature. Alright, so think about both those things. High ambient temperature, it's a hot environment. If we have 3 current carrying conductors, what that's going to do is actually cause your raceway or cable to heat up. So both these things are dealing with high temperature. What happens when temperature gets high to molecules and atoms? They expand. What happens when molecules and atoms are far apart? It's harder for electricity to get through. In other words, it has a higher resistance. The hotter it is, the higher the resistance of your conductor, the less ampacity can flow through your wire. So we now need to run bigger wires to correct that. How do we figure that out? If you have more than 3 current carrying conductors, you're going to check 310.15b3a, which is actually just a page or two back in your code book from 310.15b16. So that's quite simply saying if I have anywhere from 4 to 6 conductors, I need to derate my ampacity by 80%, 7 to 9 by 70%, so on and so forth. If I have a high ambient temperature, I'm going to check 310.15b2a, again, just a page or two back from 310.15b16. Okay, and you're going to find here, so what is, a high ambient temperature? Well, in their mind here, they're saying anything above 86 degrees. Okay, because now for some reason, instead of giving this to us in a percentage, they're actually giving it to us as a decimal number, but 1 is equivalent to 100%. So anything from 78 to 86 degrees Fahrenheit, I can take 100% of my ampacity. So anything hotter than that, I'm actually going to have to start derating. I go 96%, 91, 87, 82, so on and so forth. Don't worry if you're in a cold environment, you're not actually going to boost your wire up in ampacity. That doesn't really apply to us here. So anyway, let's throw an example here. I think it'll make more sense. So if I have number 8 THHN copper conductors in a raceway, I have more than 3, so I have an issue here. So what do we do? Well, first of all, how many amps could those number 8 THHN conductors carry normally? Again, where THHN, notice, is the 90-degree column. It is a copper wire, as I said. So we're using this column right here. And my number 8 normally could carry 55 amps. Okay, so let's take that value, 55 amps. Now we need to check 310.15b3a. I have 8 of them, so I'm going to come down here. I'm in the 7 to 9 category. Tells me I need to multiply my ampacity by 70%. So I'm going to go ahead and do that times 0.7. And of course that comes out to 38.5. So that number 8 wire, because I have 8 of them in the same raceway, is now only good for 38.5 amps instead of the original 55. Okay. Same story. Let's look at a high ambient temperature. I have some number 12 wire copper conductors in an area that's 110 degrees Fahrenheit. So it's running hot in there for whatever reason. So again, first thing, what could I normally take as my ampacity? So again, we have THHN, we have copper wire. So we're in this particular column. My number 12s are good for 30 amps. Okay, now wait a minute. We already said number 12, the biggest breaker we put it on is a 20. Well, in this case, this is where sort of this higher value actually comes in our favor. Okay, so we're going to take the 30 amps at face value, and after we derate, it may still be above 20. We might not have an issue. So we go ahead and do that. It's good for 30 amps to begin with. I come down here and I'm measuring in degrees Fahrenheit. Okay, you could do it in Celsius over here, but we usually measure in Fahrenheit. So I'm in this category. I was 110, so I'm going to have to take 87% of those wires. When we go ahead and do that out of the 90 degree, 87%, we come up with 26.1 amps. So that 10 gauge, or I'm sorry, that 12 gauge is now only worth 26.1, but guess what? It's only on a 20 amp breaker. So I got one more method I'm going to show you in another video here. We're out of time, but stand by for that one.